Hello students, welcome to the course on hydraulics FMH 202, and today we are going to start with a new chapter, that is impact of jets. To understand the force exerted by a jet on the plate wherever it impinges, we need to understand the principle that we are going to use to analyze the force. The principle that we're going to use to analyze such problems is the uh, impulse momentum principle. So, let's take it. Let's use. Let's start with our Newton's third law, that is force is equal to mass into acceleration. Further, we can convert the acceleration in terms of rate of change of velocity, and we get F is equal to m into dv dt. And if we take the time derivative to this side, then we get F dt is equal to mass into dv. Now, this expression is in fact the impulse momentum principle. Impulse is the force applied in a short duration of time. And here, this is the impulse, and here mass times the velocity is nothing but the momentum. Further, if the system has finite number of forces, it would be easier for us to use summation instead of integration. So here, if we try to integrate from velocity, from initial to final velocity, we are going to get this. And further, this is the force times dt, that is nothing but the impulse is equal to the change of momentum. Mass times the change of velocity is nothing but the change of momentum. Further, the mass is equal to density into volume. Yes. Now, volume is nothing but the discharge or discharge into time. So let's keep this time and the time on which there's a force is impinging on a plate on a surface is same. Then we get mass is equal to rho q dt. Let's substitute this mass into this expression, and then we're going to get summation of force is equal to rho q v2 minus v1. v2 minus v1 is nothing but this change in velocity, or this whole entire parameter is the change of momentum. So how to interpret this equation is forces applied on an object in any direction is equal to the net change of momentum in that direction. With this, let's try to analyze the problem. So here there is a jet and there is a plate, and when a jet impinges, when there is a jet, there's a jet impinges on the plate, the water flows along its surface, and it comes out from this place. Now, to analyze this problem, we start by making a control volume. So control volume, I have been explaining about the control volume in the classes, where it is the controlled surface area where the flow is taking place, right? So to analyze this problem, let's draw this control volume, and let's understand from where there is a momentum flux into the control volume, and from where there is a moment outflux of the system. So we know that there's a velocity that is coming in, right? This is the velocity that is coming in, and velocity that is going out from here. So this is the direction that I'm showing the velocity vector that is going out. Further, let's say because it is impinging on this plate, the plate is a reaction. There is a reaction force by the plate on the jet. That's why there's change in momentum. So that's why I have kept to a force, that is f of x and fy. These are nothing but the component of the resultant force that is acting on the jet by the plate. Now, further, we have to make some assumptions. The assumptions are, first assumption is, when jet impinges on the plate, there is no losses, there is no shock, which means it is smoothly going here and there is no frictional losses. That is one assumption. Next assumption is the height at which it is impinging and from where it is going out. This height is approximately equal to 0. Okay. Now, by using Bernoulli's principle at this section and this section, we also can conclude that the velocity that was coming in is equal to velocity that was going out. Now let's apply the Bernoulli's principle at this point and this point, and you see the pressure here is atmospheric pressure as it is coming out of the nozzle. So here is atmospheric pressure, here is atmospheric pressure. So both the side is atmospheric pressure, it goes off, and velocity head is v in square by 2g, and velocity going out is equivalent to more or less equal to approximately equal to v out square by 2g. So we get a conclusion that the velocity going out and velocity that was coming in is, it's more or less same. So these are the assumptions for all the analysis that we do henceforth. So these are the analysis that these assumptions are valid. Further, we can break this velocity into components in x and y direction if we wish to, or else we can directly analyze by taking this plane. So what I have done is I am taking two plane, that is n-axis, which is perpendicular to the plane, and p-axis, which is parallel to the plane. By the way, this is the control volume. This blue shaded place is the control volume, which indicates the water is flowing from here and going out. To analyze this, first thing first, there is the angle theta. This theta is the inclination of incoming jet and the plate. The outgoing velocity has no component in n direction. So velocity which is going out has only in p direction, which means it has no component in perpendicular direction. That is what it is. And the incoming velocity has in p direction as well as in n direction. So I'm breaking this incoming velocity into p-axis and n-axis. As the jet strikes the plate, it splits into Q1 and Q2, which means, let's say this splits, let's say the portion of discharge is going from here, the portion of discharge is going from here, and from the continuity equation we know that Q1 plus Q2 should always be the actual Q that was coming into the system. That is the continuity equation here. The magnitude of velocity, incoming velocity equals outgoing velocity, so which we have already proven with this. And this is the reaction force. In my earlier diagram I broke this force into two components. I resolve this force into two components, that is f of x and f of y, but here I'm taking as one force. This is valid. Okay, this is also valid, the other one is also valid. Anyways, you can choose. Just for a reference, I'm making this figure here. And now let's apply the impulse momentum principle. Net force is equal to net change of momentum in that direction. That implies that force in n direction, n is n-axis, okay? Force applied in n direction is equal to net change of momentum in n-axis. So with this, let's say f of x, okay, that is there's only one force, so whether you put summation or not, it is just one force. That is momentum going out of the system in n direction minus momentum that was influx momentum in this n direction, okay? Now let's say f of n, I will explain why the minus is coming. F of n is equal to the force that was going in n direction. So as I said, the velocity or the momentum that was going out, since the velocity component in n axis is 0, so going out becomes 0, minus coming in, this is coming in, v minus v sine theta. This is the component of velocity that is coming in, times mass is v rho q. Here negative here indicates that these forces in fact exerted by the plate on the vane, okay, or by the plate on the jet, and we are interested to find the force that is exerted by the jet on the plate. So these two forces will be equal in magnitude but opposite in direction. Further, let's say in p direction now, the summation of forces in p direction is equal to net change of momentum in p direction, right? This is the same as this one. So summation of p is equal to p out minus p in. This p means the momentum flux going out of the system in p direction, momentum flux that is coming into the system in p direction. So here one more thing is there is no forces in p direction, so I'm saying 0. By the way, can you digest this? No forces in p direction. However, there is a change in momentum in p direction. We have already said a force must be applied to cause the change in momentum, and here I'm saying there is 0 force. So if you have this doubt, I would like you to analyze this for yourself first. If you still cannot figure it out, then we can discuss over the WhatsApp. Okay, so for now let's understand that there is 0 force, there is no force in p direction, so 0 is equal to p out. Now see, Q2 is going from here, Q1 is going from here, right? So in earlier case, both was, I mean, in from n direction. In earlier case, in n direction, it was nothing was going out, right? So here, let's forget about the earlier case. Let's continue with the new this one case. So 0 is equal to, now I can make the density common, and velocity common, and it has to be, I can take it this side, so it becomes 0. So Q1, now here minus Q2. Why there is minus Q2? Going out means it is going out, it's going out, it should be addition, right? But here it's going out because of this sign convention. This is in negative direction, that's why v is in negative direction. This is positive, this is negative direction. Minus vq rho q v cos theta. This is what is coming in, this is what is coming in v direction. So from here, we know that the ratio of Q1 by Q2 is equal to 1 plus cos theta divided by 1 minus cos theta. So for this, I'm stopping here and we'll continue in next video.